For more paleoseismology also found some earthquakes in the past, but a large part of the seismic cycle we don't know anything about yet. And that's where the seismothermomechanical comes in, that I'm gonna use. And this model can simulate the earthquake cycle for thousands of years. And this way, for example, we can get an idea of how representative the measurements we're doing now are for the rest of the seismic cycle. So, for example, if the interseismic signal is stationary over multiple earthquake cycles or not, and also if the seismicity changes through times. But first, a good understanding of the region is required to build a realistic model. Wait, yes. Okay, so the STM model will first simulate the geological evolution for a few thousand years with a time steps of roughly 200 years. And then the seismic cycle will be simulated with a minimum time step of 1 year. And the model will start from a geological cross-section. Here on the right, you can see an example of a similar model, but then in the northern Apennines. For now, I'm first focusing on the geometrical setup. So first, we need a geological and structural cross-section. Furthermore, information about the moho depth and geometry is required. And we need information about the lithospheric structure, for example, how the plates are overlapping, and if there is even an active subduction underneath the central Apennines. So to constrain this, I've been reading a lot of papers, and I will share with you some interesting findings I found. First, the main deformation mechanism in the region is still debated. There's extension, which is localized on the crest of the Apennines. And furthermore, GPS has showed that the Apennines are uplifting. And then there are different hypotheses about what causes this deformation. The first one is a difference in gravitational potential energy. And this would explain why the deformation is localized on the crest of the Apennines. Furthermore, dynamic mantle support has also been suggested to cause the uplift and extension, or a rotation of the Adriatic plates, or maybe a combination of all three, which is most likely in my opinion. Then there's a question about the uplift of the Apennine chain. GPS studies argued that the entire Apennines are uplifting with 1 to 2 millimeter per year. However, the new in-source study cannot confirm this geodynamic uplift. Here you see the uplift from that study. So uplift will be more orange-red, but in general, it even shows more subsidence than uplift. So the question is there really a geodynamic uplift in the Apennines or not? Furthermore, the strain in the Apennines, in the central Apennines, the strain is distributed over several faults, as you can see here. But in the northern central Apennines, it's localized on one fault system. And this raises questions about how stationary this signal is over multiple earthquake cycles. Because if it would be stationary, you also expect differences in topography, but this is not what is observed. And last, there's a slab window proposed under the central Apennines. For you who don't know what that is, that's the location where the slab is interrupted. Here's a sketch of such a scenario, where the slab is still attached under Calabria and the northern Apennines, but not under the central Apennines. And this is supported by an absence of deep seismicity, a lack of compression, tomographic anomalies can also be explained by compositional and hydrational differences. So it's not 100% sure yet if there is even a slab window under the central apennines or not. And this poses some challenges for designing the model setup. First is the large variation along strike. So currently I'm thinking about designing two models, one in the area with distributed deformation and then one in the area with localized deformation. And because the deformation is still debated, I want to test different hypotheses with the model. And also, for example, with the slab window, I'm thinking about doing a model with slab and without to see which one can reproduce the current deformation that we observe. So what I will do in the coming weeks is install the model code here on the server at Easter and do some test runs with the Northern Apennines model that already exists. I will also assemble all the data of the Central Apennines in ParaView or QGIS, and I will continue with designing the model setup. And that's it.
Okay, thank you, Michi. Any questions? Or I have a few, but questions by anybody?
Yeah, I have a question more the longer term about the longer term plan here, because you're of course using the the existing model with the long time steps in the beginning and the short time steps afterwards. But what I'm of course working on is trying to integrate the adaptive time stepping for more complex settings. So do you know if the idea is to in the end also try to use an updated newer version of the model when it exists in some years for the Apennines?
Yeah, I think the idea is to do that, but it depends on like how much time that will take you, because of course we want to start as soon as possible with the model, and I cannot wait for 2.5 years to
of course
to do that. But yeah, the idea is for sure to use the updated model once it's ready.
Okay.
But I think that would only be like just rerunning the model with the updated code and reanalyzing the results.
Yeah, seeing if there's anything additional in there. Okay.
Yeah, see if if simulating the seismic waves as well will change the results.
Good. Any question? Anybody else?
I have a question, if I may.
Oh, yeah.
Yes.
Super interesting project, and I love the that image with the faults and the deformation and that distinction you pointed out between more in the north where it's all localized on one structure, and in the south where it's more distributed. And it reminds me a bit of the San Andreas fault, where in the north also it's more concentrated and it's more distributed across wide shear zone. Although that's strike slip fault, so very different tectonic regime, obviously. But I wonder, to what extent is this reflected in topography? So are there very systematic differences also then in topography that?
No, there are. I mean, I didn't look into it myself, but the paper that raised this question said there was no significant change in topography. So that's why it's the question how representative this is for the long-term strain distribution. Because if it would always be like this, you would expect changes in topography along strike. But that is not what is observed. So it might be only a temporary thing.
Okay.
Could it also be that the deformation is dominated by something that's not happening on the faults, like a more I guess some of the slab window hypothesis, for example, and I know very little about it. I'm just thinking about here.
Yeah, so that's one of the hypotheses, that the slab window causes more a sinusoid upwell, which uplifts the Apennines and also drives the extension. And that's one of the hypotheses I want to test with the STM model.
Cool. Very interesting.
Actually, about the model, can I ask maybe a couple of questions, Mikey, about how you will in the end simulate the seismic cycle? How does that work? I mean, is there some friction in the model, or how does that work?
Yeah, there's a slip rate dependent friction in the model. So when the slip rate increases, the friction drops, and this allows for spontaneous rupture propagation.
Okay, so actually, do you simulate like rupture propagation then, or I mean, basically the question is whether you can have different size of earthquakes in this type of model.
Yeah, so the model does not simulate the seismic wave propagation because the smallest time resolution is 1 year currently, but it does simulate areas of localized strain and with higher slip velocity. And then in the post-processing, you can filter on slip velocity and stress drop, so you can see where the earthquake propagates.
But okay,
Is that clear or not?
I have a small question. No.
Yes.
Can you hear me? No.
Yes, I hear you.
Okay. It was about the rheological properties you are using for your crust, your lithosphere. What do you have in mind? For example, I don't know, the Central Apennines, I think is I mean, it's not so easy to understand how is
No, that's
how is the crust, in fact, because there is not much information in there, let's say.
No, that's also gonna be a challenge indeed. So I will try to constrain it as much as possible with existing literature, and otherwise maybe I will use some default.
Yeah.
There are some pretty explicit 3D models of the lower crust. It's just that they're very debated, I think. I've seen people argue at EGU. And so depending on which model you use, some people will have objections, but that's always the case.
Yeah.
Okay, thanks. I think we missed David.
I think
he has some problem with the connection. I don't know.
I'm having some Wi-Fi problems.
Laura, yes, Laura, go ahead.
Yes, nice to meet you. I just have a comment. During your presentation, you mentioned the stationarity of the process in producing earthquakes. So I just want to stress you that the meaning of stationarity is something very different from a regular occurrence process. So keep this aspect in mind when you will be sampling your delta time, your interval of observation in the model. I think it's very important to have clear in mind what stationarity means and how it behaves in a model. It was just a comment. Very
okay. Thank you. And what is the definition of stationarity according to you?
Well, of course, when we are dealing with the seismic process, stationary is something that occur, let's say, randomly, and in which the mean occurrence time of something has the same variation. The variation is equal to the mean. So stationarity does not mean that you have a fixed recurrence time for earthquakes, but earthquakes that occur randomly, but with a given range of variation that is represented by the mean occurrence time. So what is the implication in the model? Really, I do not know. But if you are modeling the evolution of the geological process in a way that does not represent the full variation of what you are expecting, probably you are doing not a good job. I'm talking without any experience of how this kind of modeling behave, but just to make clear that some definition has to be deepened when you use it. Okay. I see your face.
Yeah, my connection is not that good. But thank you for the comment.
Okay.
Okay. As I said, we missed David, but I don't remember. The plan was you did both the presentation of the students, so I think we can start with Michele. David is connecting just now. Okay. We missed you, David.
Yes, I get disconnected. I'm not at the lab. I'm in some, conference center, and it doesn't work well.
Okay, don't worry. And so the plan now is to start with Michele presentation.
Yes. So it's over to Michele, and so the idea of the lectures is again, for you, all the DC is to learn things, and so it's important that everybody can ask questions, and don't hesitate to interrupt Michele if you feel like the need to ask questions during the lecture, and then that's it. And so Michele, I don't know.
Yeah, I can share as in my screen.
Yeah, you should be able to share a screen.
You see something? No.
Yes, I will stop with my microphone because there's quite a lot of people in that room, so it's a bit annoying. And it's over to you now, Michele.
Okay, thank you. Can you see my screen? Yeah.
Yes.
Okay. So good afternoon, everyone. I'm Michele Fondriest from University of Padova. And
Michele, just one thing, you're not in the full diaporama mode.
No, I need to move it here. Probably I need.
So we can
Maybe you have two screen.
Yeah,
two
it's a screen. I move
yeah.
Here. Yeah. Should be okay now. Is okay now?
Yes, it is. Yes, perfect.
Yeah, I just detach the screen. Sorry. Okay. So I'm Michele. Nice to meet you, all of you. Thanks for the invitation. And I'm just in this lecture and just put together some material about the architecture of fault zones. In particular, put together some material that I think is something that needs to be known, let's say, about the structure, internal structure of fault zones and their mechanics. And in this sense, since I think the background of all of you, PhD, I think is a bit different. The presentation is a bit of general in some sense. So some of you may already know some concepts. Hopefully not all of you. And yeah, and then just yeah, if I put together a bit of material, a bit in a rush, so if I'm a bit messy or if you don't understand anything, just stop me and ask. Yeah. Okay, so architecture of fault zones. I see that many of you, I mean, are going to have as a target area for your PhD studies the Central Apennines of Italy, and this one, for example, in your view, is seismogenic normal faults, the Monte Marine one, which is nearby L'Aquila, like 10 kilometers to the northwest. You can see the main fault surface here, and then a natural cross-section through the foot tour of the fault zone inside what is called the fault core. And this, for example, is a fault that ruptured in historical time during the 1703 earthquake that destroyed L'Aquila before the last event of 2009. So faults, what are faults? In very general view, like faults are localized and narrow in a relative sense zone where the deformation of the crust is mostly accommodated, even at a lithospheric scale. So, for example, you can have this kind of faults, which is a very big fault, which is in fact is a plate boundary, and probably is one of the most famous faults in the world, which is San Andreas, which in fact is accommodating strike-slip deformation along a complex plate boundary between North American plate and Pacific plate. Then if we move more nearby us in the Mediterranean area, again, you have faults of different hierarchy and different importance, let's say. So you have again plate boundary faults, the North Anatolian faults, the East Anatolian faults that rupture in this February, in a big earthquake, in a series of earthquakes up to 7.5 magnitude. Then you have another big plate boundary with the Hellenic subduction. And then you can see instead other small faults here, more to the north to the Hellenic subduction, which are not really plate boundary faults, but still connected to plate boundary dynamics. And in fact, if we, for example, focus here, all these faults are faults related to back arc extension, which are, for example, here accommodating the opening of the Gulf of Corinth. And here, before we are having like faults that were at lithospheric scale and 1,000 kilometers long, here you have faults that are on average from 5 to 30 kilometers seismogenic. So if you look, for example, on one of these fault exposed in inland, you have this kind of exposure from the paper of Wall et al. 2020. This is the Sinos fault. This one with a fault probably is like 15 to 20 kilometers long, and you can see that is an extensional fault with a nice fault surface with deep normal grooves, and putting contacts Triassic carbonates in the footwall with quaternary deposits in the hanging wall. And if you have a look really on the fault surface, you have this kind of material. So we'll have a super localized and sharp surfaces. And below, you can see that this surface is cutting through some peculiar fault material, which is called, in this case, cataclasite, so a cohesive rock, which comes from the comminution and crashing of the host rocks. For example, these fragments are fragments of the host dolomites in the footwall. Then if we move to something like more nearby to the place we are going to study, we are here at the tectonic map of Italy with all the seismicity till I think 2004, something like that. And in particular, you are going to focus mainly in this area, most of your projects, I think. So the Central Apennine of Italy. And here you can see in black, this is the frontal compressional front of the Apennines. And here, so you have in red all the compressional earthquake, and in blue you have all the extensional earthquakes. So you can see that in the Central Apennines, you are now in an area that is under active compression. And basically what happens is that you have a system of active normal faults, which are this one in black, these black traces here, which are dissecting a fold and thrust belt, which is the Apennine belt. For example, these blue lines here represent the trace of the older thrusts. And what happens is that starting from the axial part of the chain here, moving to the west, you have a lot of extensional faults that are now active and seismogenic. For example, these are all the bits ball, let's say, of the focal mechanism, the main shocks related to the last big earthquake sequence that struck the area in 2016. And here in red is the trace of the rupture surfaces that rupture all this fault system. And if we make like a section through this area, what we have is something like that. So we have, as we were saying, a fault and thrust belt. So these are the thrusts. Moving to the west, you are moving toward the out of the screen, let's say, to the Adriatic side, so to the active compressional front of the Apennines. Here, clearly the thrusts are inactive now, but starting from the axial part of the chain are cut and dissected by this system of normal faults, which are seismogenic. So this is the fault that ruptured in the last 6.5 North earthquake, 2016 in October, was a normal fault. And looking like in a field view, this is the kind of surface rupture you get in the area. So a lot of segments overstepped each other. And here you can see faults, which are in this case up to 20 kilometers long, the fault system that ruptured with a reactivation of a fault plane with a carbonate footwall. And here, this whitish part represents basically the coseismic displacement, which was up to 1.5 meter locally. Then, when we go in the field as structural geologists, we are studying these big faults and entering inside what is called a fault zone, and we are normally able to measure structures that are even smaller, so faults, a fault zone which are tens to hundreds of meters long. For example, this is an example of these older thrusts outcropping the Central Apennines with a classic duplex geometry. And this is an example of a small extensional faults here with a very little displacement. So just to say that faults, I mean, are all over the scales. I mean, important thing is that faults, as we are saying, are narrow. I mean, kind of tabular bodies, narrow in a relative sense. I mean, bodies which are accommodating most of the formation in the crust up to the entire lithosphere, if they are like plate boundary faults. And they are fundamental because they control the mechanics of the crust and their fluid flow properties. So to talk about this, we need to talk about this kind of schemes, which maybe you are familiar with, which is a general example from Kolst et al. Of a lithospheric strength profile. So this is a case of a continental lithosphere. And you have this envelope here, which represents basically how much differential stress your crust, your lithosphere can sustain with increasing depth. And you can see that this envelope has different shapes. So you have this initial part here, where you have a linear increase, differential stress with depth, where you have you have a frictional, let's say a frictional, brittle frictional regime. In the case we are talking about the fault, so let's say we are missing here a cohesive term, so the cohesive term is not so relevant. What you are having, that's the strength of your crust and the strength of the fault, or the crustal fault, is controlled by the static friction, the normal stress, and the pore fluid pressure. And from experimental studies, we know that for most of the rock, this static friction is in between these values, so between 0.6, 0.65, 0.8, which is a Byerly friction is called. This is after a seminal paper of Byerly in 1978. And this kind of this kind of profiles are based on experimental, all about experimental data. Experimental data coming from rock deformation experiments. So typically, the mechanical behavior, the rheology, let's say, of the crust is approximated by the rheology of quartz, so monomineralic, let's say, crust. and then the mantle, the upper lithospheric mantle by olivine, for example. So typically what you have is like at around 300 degrees C, which can be around 11 kilometers for a continental lithosphere, where you have like 30 degrees of thermal gradient. You have what is called a brittle plastic transition. So the deformation in the crust is not anymore happening by fracturing, by faulting, but your rocks are starting to flow by this kind of flow can be described by different flow laws that have this kind of form, which is a typical Arrhenius type relation. So it puts in relation the strain rate at which the rocks deform with temperature, with differential stress, and with different other parameters. For example, this is a flow law for grain size insensitive creep. This one instead is sensitive to grain size, and it's a typical flow law for dissolution precipitation creep, which is a very important mechanism for fault zones in the crust. So just to say that when we think about faults in the crust, in the lithosphere, we need to think about this lithospheric strain profile, also because this kind of profile will also determine which kind of is associated with the kind of deformation mechanism are active within the faults, and at the end also with kind of fault zone structure we have at different depths. So the point is here is that by changing the lithology, for example, this kind of envelope will change. By changing the tectonic setting, the envelope will change. By changing the thermal gradient, the envelope again will change. So in our case, in this presentation, we are going to focus about brittle fault zones. So in this part here, let's say, so in the brittle crust, and at the beginning when we start to have, let's say, the brittle ductile transition. This why, because in this area is where the crust, let's say, can sustain more differential stress, and it normally is representing the base of the seismogenic zone. So in fact, then if you look inside of this brittle crust, the things are still a bit more complicated. And these are the results of a quite recent paper, which show, in fact, that, let's say, the deformation behavior of the crust and a crustal fault, in this case, will be dominated by friction and faulting in the upper part. But then you only need to consider the flow law of your rock. So what is the crystal plastic deformation of your rock, but you need to consider also the yield stress of your rock. So where your rock will start to deform in a ductile form. Ductile deformation means distributed deformation, which can be accommodated by microfracturing, so by brittle mechanism, but it's still brittle deformation. Instead, for flow stress, here we mean when we start to deform the rocks in a crystal plastic behavior. So if you think of a crustal fault going down with depth, you will move from an area here where your deformation will be like purely frictional. Then you will move in this area here where you have a brittle ductile behavior. So you will have frictional behavior on your fault, but a lot of microfracturing around. And then we go even down, you will move to a brittle plastic transition. So you will have both diffuse microfracturing, and you start to have also crystal plastic deformation going on. So everything is more and more complex. So this is the case, for example, of Carrara marble. So for example, of a carbonate crust, which can be the one you have in the Central Apennines, just without considering the effect of temperature, if you are applying in the lab 100 to 120 MPa of confining stress, which means between 4 and 5 kilometers of depth to your rock, you will start to have not only frictional behavior, not only faulty, but you start to have a lot of ductile deformation around your fault in terms of microfracturing or twinning, for example. Then if you go down, you start to have both, I mean, let's say, delocalized and diffuse deformation in terms of microcracking, and start to have crystal plasticity. In the case of silicatic crust, in the case of quartz, you will have a kind of frictional ductile deformation till here, and then you will start to activate quartz crystal plasticity around 300 degrees C. So then another complication is that your frictional behavior will be different in different tectonic settings, in the sense that in different tectonic settings, the mean stress is different. So the mean stress in general is higher in a thrusting regime compared to a strike slip one and a normal faulting regime. So if you then want to try to draw, let's say, a kind of fault zone structure scheme at the crustal scale is a bit difficult. So this kind of scheme comes from Fager et al. 2011, but it's basically very similar to what was proposed in the 80s by Rick Simpson, by Chris Scholz, which are very big seminal papers, this one, to have a look. So you will have this kind of structure. So you will have an upper part of your crustal fault where you have brittle deformation and brittle deformation. Then here you can have brittle deformation plus ductile deformation in terms of microfracturing. And for example, if you have fluids, you will have dissolution precipitation mechanism going on. Then when you start to have to activate crystal plasticity, for example, in quartz, you start to have viscous deformation in rock. So you start to have different kind of deformations. So you can populate this kind of fault zone structures with different fault rocks, which are the rocks that accommodate the deformation in a different depth along this fault. So in the upper part, we will have what we call gouges, rock fault gouges, which are rocks, brittle fault rocks, very, very comminuted and unconsolidated. Then if you go more in depth, you will have the effect of fluids. So you will have what we call cataclastic rocks, which are still crushed and comminuted fault rocks, but cohesive, that can have foliation, so different fabrics, or can be more isotropic. And then if you go down in this regime where crystal plastic deformation is dominating, you have what we call myelonites, which are completely rocks where the deformation is completely viscous. So most of the components, most of the minerals composing these rocks are deforming by crystal plasticity and not by brittle faulting, brittle fracturing. So the point is that this is a nice scheme, but in fact we know very little about how true is this kind of fault zone structure conceptual model, especially how is changing the thickness of the fault zone going down in the Earth crust. This is why because as structural geologists, we just study faults exposed in the Earth's surface now, which are exhumed from different depths. So we can have a view, for example, of a fault zone which formed by faulting, I don't know, at 2 kilometers depth. Then we can have another outcrop showing a fault zone which was formed, I don't know, at 9 to 10 kilometer depth. But it's basically impossible to have a single fault structure exposed over crustal depth. We have some information from drilling projects, but they are very local. We have some information from geophysics, but the geophysics normally doesn't have the resolution to image really the internal structure of fault zone over crustal section. So we go basically back to this kind of drawing of Simpson of 1980, where we have different crustal fault zones in different tectonic regime, for example, compressional, strike slip, and extensional one. We have here in dotted line what is called brittle fault zone. So our brittle seismogenic fault zone in the crust, and this one instead with lines in represents the root, the viscous root of a crustal fault zone. And you can see that also at the time Simpson was making different hypotheses, but we are basically at the same level now, because we cannot say if normally, I mean, the viscous root of a thrust zone is like this, or the same was in the other contexts. So just to make things a bit clear, now we are in this presentation, we will just drop completely this part, so the viscous roots of our crustal fault zones. But we are going to talk about brittle fault zones, so the forming by brittle deformation in the upper crust. This is another important point to say. So before we were just saying, talking about lithospheric strain profile and how the faults control basically the strength and the mechanics of the crust. And you were saying that in the brittle regime, basically the behavior is a frictional one, which is controlled by a Byerly friction, which is around 0.6. And that was determined just by experiments from Byerly. This is another piece of evidence that these things are true. So these are data coming from the seminal paper of Townsend and Zobach, which shows basically measurement of stress, deep measurement of stress in the crust, different depths and different location. And you can see that basically they kind of agree with this kind of frictional behavior, this Byerly frictional value. So the point here, just to stress again, is just that the magnitude of stress in the shallow crust is controlled by the frictional strength of the fault, so by frictional behavior. And the other important point is that the mechanical properties and the strength of the fault at the base of the seismogenic zone is the one that controls the strength of the crust. So after this brief, let's say, introduction, I will now describe you a bit the outline of this lecture. We will be like giving you a few hints, a very basic concept of what is a conceptual model nowadays, let's say, of the internal structure of brittle fault zones. Then we will have a look at what are the controlling factors of this internal brittle fault zone architecture, and, for example, scalar relationship of different components of the fault zones. Then we will have a look at how tectonic settings can influence the fault zone structure, how the formation processes also can be associated with different fault zone structure. And at the end, we will make a link between fault zone structures and the seismic cycle. Just to start, this is the classic model we have from the seminal paper of Kane et al. 1996, or the structure of a brittle fault zone, which is basically constitutes, is made of three main components, which is the fault core, this one in a more in dark color, which is the zone of the fault, which accommodates much of the displacement, most of its displacement, most of its shear deformation. Then this fault core is embedded inside a zone which is called damage zone, which is characterized by a much lower level of shear deformation, much more distributed deformation. And typically the fault core is made of crushed, let's say, fault rocks. So rocks coming from the crushing, a comminution of the original host rocks, and is characterized by a very low permeability. Instead, the damage zone is characterized by subsidiary faults, secondary fracture, veins, for example, and is generally characterized by higher level of permeability. Then when you move outside of the damage zone, you are moving to what we call the protolith or the host rock, which will be characterized by background deformation. So just to have a look at what can be like some picture of these different fault zone products. These are, for example, some picture of fault gouge materials. This comes from silicatic rocks, so is a fault gouge by definition is a crushed rock, comminuted rock, which is unconsolidated, so is uncohesive. Can be homogeneous in texture, can be more anisotropic, so can have some fabrics related to the movement of the fault. This, for example, is another case of a fault gouge, which is basically a powder of carbonate in this case. Then you can have cataclasites, again in silicatic rocks, like in this case, or in carbonate rocks. These again are rocks deriving from the fracturing and the formation under shear of your rock, but differently from fault gouges, these are cohesive. So they are normally related to some kind of cementation, so some kind of fluid rock interaction also. And then you move to damage zone. When you move to the damage zone, again, this is a case in silicatic rocks, so in granitoids, these are cases in carbonates. Basically, what you will see is like you can see volumes of your intact or host rocks, which are still preserved, and then you will have the rock which is cut by secondary faults, by secondary fractures, by veins, and so on. For example, this is a case of a carbonate cut by dolomite vein. The important thing here, as you already can appreciate, is that this very basic conceptual model of fault zone structures is influenced by many factors, which are, for example, lithology, the dimension of your fault, the type of fault, so the kinematic of the fault, the pressure and temperature condition at which you are having your faulting, let's say, when your faulting is occurring, and, for example, the amount of displacement, so the structural maturity. This kind of fault zone model was developed basically at the beginning with an objective view to describe the fluid flow regime within a fault zone. No? Is still valid, this kind of description of fault zones. In fact, is used by everyone. Why? Because it's simple, because it's, I mean, you can always in the outcrop recognize a fault core, a damage zone, but it's a kind of a static view. So it doesn't give you any idea, this kind of model of Kane et al., of how these different fault zone units are distributed in space in general. So as I was saying, this model of Kane et al. Was mainly developed for explaining fluid flow within fault zones, brittle fault zones. And they basically recognize some different type of fault zone and members, depending on the different percentage of damage zone versus fault core within your fault. So you can start with, in this area, with what they call a localized conduit. So basically a fracture, as my fracture, which is open, and you don't have basically any fault core. So this can be a case, for example, when you go in the field of a small fracture, which is permeable, doesn't have any fault, doesn't have accommodated much slip, and you don't have any gouges or cataclasites along it. Then you can have otherwise a situation in which you have a more distributed deformation. Again, no fault core, mostly damage zone, and this is a typical case of fracture corridor, which are very studied, for example, in hydrology or in the oil industry. And then you move to this kind of more combined fault zone scheme, which is, I would say, the most common and the most crustal fault zone, where you have a fault core, which is mostly impermeable, surrounded by a damage zone that is normally very, very permeable. So this is a very basic model again, I'm saying. Then we move to a bit more, let's say, sophisticated model, but still a very conceptual model. This is after another big seminal paper of Faulkner et al. 2010, where basically he recognized two types of fault zones, crustal fault zones. So a fault zone where you have a single fault core with very localized deformation, normally fault cores of tens of centimeters to meters thick maximum, and surrounded by damage zones which can be hundreds of meters thick. And in this case, we are just showing a model in which, moving away from the fault core within the damage zone, you will have like a decrease in fracture density and clearly also a decrease in permeability. You will see that the fault core is the less permeable unit inside of your fault zone. And then with the progressive decreasing of fracture density in the fault damage zone, also the permeability will decrease toward the level of the host rock. Another more complex, fault zone structure is this one, where you have a much thicker fault core, which can be up to kilometer, up to 700 meters, up to 1 kilometer thick. You can have different fault strengths where most of the shear deformation localized, and most of the cases these are fault gouge strengths. And then you can have a damage zone around, it can be again on the order of several hundred meters thick. And here clearly then the damage structure and the permeability structure of this kind of fault zone will be very different from the other one. These two models are not, let's say, random, but were inspired by two big fault zone, crustal fault zone that, let's say, were described by the first people that started, let's say, in our community of structural geologists and rock mechanicians to study really and to try to quantify the structure and the mechanics of brittle fault zones. And these two faults are this one on the left, which is the punchable fault, which is an exhumed strand of the San Andreas fault. So one of the most studied fault in the world. And this fault is exhumed from 2 to 4 kilometer depth, has accommodated 40 kilometers of displacement, and is mostly is a strike slip fault. And is developed inside silicoclastic rocks. So you have here granitoids in the hanging wall, and here very tight sandstone in the footwall. The kind of fault zone structure you have is like a very, very localized fault core, which is up to 20 centimeters thick and is made of ultracataclasites, so very, very high strain fault rocks, cemented in this case because is a fault which is exhumed from a few kilometers of depth, is not very superficial. And then you have another case of fault, which is the Carboneras fault, another big strike slip fault. Here you are in southern Spain. Again, the rocks, the host rocks are silicoclastic rocks. The displacement of the fault is exactly the same. The exhumation depth is very similar to the one of the punchable, but the structure is completely different. Here you have up to 1 kilometer thick fault core, and you have here a lot of different strands of gouges, which are accommodated the deformation in a much more distributed way. So it's exactly, if you want, let's say the actual, example of these two model, of very localized fault core and very distributed deformation. So these start to suggest you that another important factor in controlling the structure of a fault zone lithology, but the relative mechanical properties of your. In particularly here, the fault zone is developed inside mica schist, which are very anisotropic and foliated and weak fault rocks. And so when you are producing and developing a fault zone inside this type of rocks, the formation will be much more distributed compared to a fault zone, which is instead developing within a strong granitoid. So fault zone structure, what does it mean in my view? Basically, quantifying the fault zone structure means to reconstruct and to quantify the distribution at a certain depth of fault zone products, so fault core, damage zone, and so on, together with their mechanical properties, so mainly elastic properties and frictional properties, and transport properties, which means mainly permeability. This is a case, for example, of a section of fault zone in the Central Apennines we studied in the years. Is a fault which is almost 20 kilometers long, and there's extensional faults exhumed from 2 kilometers depth. So it's put in contact quaternary deposit with the form, the footwall block, which is developed inside tight and very strong carbonates, which are dolostone in this case. You can already see inside the footwall that you have different colored units, which are separated by sharp boundaries. And for example, we did the mapping inside here, and this yellow unit here is what we call a fault core unit, which is made of cataclasites. And instead, these green and blue units are fault damage zone unit. So where you can still see the host rock deformed by several subsidiary faults and fracture, but you don't have a very crushed and comminuted rock which accommodated a lot of shear strain. So the point here, again, here we are applying the same model before, Kane et al. So just describing what is our fault core, what is our damage zone, what is their extent. But then the new passage then is to try to study this kind of fault structure where they are exposed for many kilometers along strike. And this is the case of this area. So this is just a section that we mapped, but we could map this fault zone along almost 2 kilometers along a very well exposed area. So we can have a kind of a map view of our fault zone structure, which was exhumed from 2 kilometers depth, and have an idea what was what is the fault zone structure at this depth. And so what you can start to appreciate here that these yellow units that we were saying before are the fault core cataclastic units. They are changing in thickness, for example, along strike, and the same is for the damage zone units. Another important point, we can start clearly to map all along our strike the principal fault. We can start to map also in the footwall the subsidiary faults and see how the geometry of these faults changes and how these faults are bounding different fault zone structural units. And then here with this whole figure, we are just able here to show, what are at the mesoscale different type of structural measurement we can take. So for example, the attitude of different faults, their kinematic, and start to reconstruct, let's say, in a 3D way, the fault zone structure in terms of fault zone rock distribution and also geometry of the fault and fracture network, geometry and kinematic. So that's, let's say, in my view, what should be, the way of quantifying in a modern way, like a fault zone structure. So not only studying in a section, let's say, the type of fault zone rocks and their thickness, but also try to describe, to quantify the distribution along strike and possibly also down deep. And then the other point is to try to merge these with the quantification, a proper quantification of the geometry of the fault and the fault network in 3D. And historically, this is a bit a problem because let's say the communities that are studying the fault zone rocks and the formation mechanism are structural geologists more related to rock mechanics. Instead, the community they are instead like say quantifying and describing in a quantitative way the geometry and of a fault and fault zone network is in 3D is more a community which comes from the study of faults related to the oil industry, for example. So people that are studying faults not only in the field, but then in seismic reflection data, for example. So the important thing is that then we need to quantify also the geometry of fault zones in the fault fractal network in 3D. And this is connected directly with the concept of fault segmentation and fault growth, because as we saw at the beginning, a fault, in fact, is never a single fault, but is a fault system, the one that is active within a region. And normally faults are growing as different segments, and then they, during their growth, they start to interact and give birth to interconnected and complex fault networks in 3D. So we can try to do it from field data, but then there is a lot of people that does wonderful jobs about describing and quantifying fault zone network in 3D based on seismic reflection data. And what they do very well is like reconstructing fault zone surfaces in 3D and how the displacement distributed and is in 3D along faults, because clearly a fault but the displacement in a fault is not the same along all the faults, but will be maximum in certain area and will go to zero at the extreme of the faults, the fault tip, what we call the fault tips. So what is important to do is like putting together distribution of fault zone rocks, geometry and kinematic of the fault zone networks, and at the end also, for example, the topology of the fault and fracture networks, which means how basically the different fault segments are in contact one with respect to the other in space. And there are different groups that are working in this kind of topics, and in particular about quantifying fault network topologies. For example, there is this group of Gundenberg and many others, and there are even algorithms like tools to do it automatically now. This is an example of a mesoscale, outroscale fault networks, and a kind of study you can do in terms of topology quantification, which at the end goes again towards studying fault network connectivity, and at the end, if you want, also fluid flow models within fault zone. You can do it at the meter scale, and then you can try to do it at the scale of the entire fault system, so at the kilometer scale, for example. So now, after this brief section, I'm going to show you and discuss a bit briefly what are the main controlling factors that the factor that controls the architecture and internal structure of fault zones. So the first one, for sure, is the lithology, so the host rock lithology. which, as we can see, is also related to the depth at which the faulting happens. For example, if we have very porous lithologies, which means normally rocks which have more than 10–50% porosity. So this means porous sandstone, calcareenites, for example, or volcanic clastics. We typically have this kind of fault zone structure in which we can have a principal fault and then very broad fault zone associated to the principal fault. This is because mainly the deformation inside the fault zone and the damage zone is not accommodated by discrete fracture, but is accommodated by these different features which are generally called deformation bands. Deformation bands are basically planar structures accommodating shear strain deformation in porous rocks, which are generally accommodating much less displacement than a brittle fracture, and are associated generally to a porosity collapse, and so a compaction of the rock and a reduction in permeability. So what you will have when you have to you deal with very porous rocks, which are generally present in this condition of depth, so less than 1 kilometer. You will have some fault zone which are broader and characterized by much less intense deformation inside the fault zone compared to fault zone developed in non-porous rocks, both carbonates or silicoclastics. Clearly, given the same condition of displacement and let's say accommodated shear deformation. Then if you move inside non-porous rocks, this could be the case of tight carbonates. This is a case of a small fault exhumed from 2 kilometers depth. You can see that you will have a principal fault surface with different segments, a kind of fault core developing here, where the rock is fragmented. And all around, you can see what we call a damage zone, so an area where you can see still the structure of the host rock, the bedding, but you can recognize a lot of subsidiary faults and secondary fractures. In this case, this is a fault which is very small displacement to accommodate a very little shear strain, probably less than 1 meter. But then if you go to a much bigger fault zone in the same kind of lithologies, again, is a fault zone exhumed from the same depth, so you can compare the two faults. What is changing completely is the displacement accommodated. You have a much wider fault zone. This is the case of the Venere fault, which is the seismogenic extensional faults in the Central Apennines. And you can recognize a 1.5 meter thick fault core made of cataclasites and ultracataclasites, then a several meter thick zone of pulverized or shattered carbonates, and then you move inside of a 100 meter thick zone of intensely fractured carbonates, where you can see secondary order faults. For example, if this fault is accommodating 600 meters of displacement, these small faults can accommodate up to 100 meters thick or several tens of meters. And here, your rock is intensely fractured by brittle fracturing. You can find some veins and so on. Then if you move in silicatic rocks, still strong rocks, let's say, and non-porous, again, we are looking here at the same fault we saw before, so the punchable fault. The depth of exhumation of this fault is very similar to this one in carbonates. And instead here, the host rocks are granitoids and sandstone. Again, you can see a localized fault core and then a damage zone, which in general is or the order of a few hundred meters thick. In this case, the deformation is very localized, and the fault core is constituted of minerals coming from the host rock, but also of minerals like clay minerals like this, which comes from the fluid rock interaction processes. And these clay minerals are weak minerals. So in this case, I mean, this is a case of a fault which is more mature compared to this, because you go from 600 meters of displacement to 40 kilometers of displacement. So you have a more mature fault zone and a much more localized structure. So a much more localized fault core and a damage zone which is for the order of hundreds of meters thick. Then if you can have a guess of how is instead the structure of a fault zone down in the same kind of host rocks, so again granitoid rocks, but much deeper in the crust. Here we have a fault, which is a transpressive fault in the southern Alps of Italy, inside granitoids. This fault is immature compared to the first fault here. So here we have 40 kilometers of displacement. Here you have almost 1 kilometer of displacement, which is accommodated over an area of 550 meters. So it's a very thick fault zone. And in fact, if you look in detail inside of this fault zone, you can see all these kind of strands. Each one of these are small faults which accommodate a few meters of displacement, and are associated to cataclastic bands of very cohesive rocks, indurated. So the host rock is a kind of granite, and the cataclasites is indurated fault rocks rich in chlorite and epidote. And then you can find also this kind of peculiar fault rocks in black here that are pseudochylites, which are the marker, the geological marker of frictional melting happening during seismic slip. So this is, for example, a view, like a picture, let's say, of what is the thickness and the structure of a immature fault zone in non-porous silicatic rocks at this kind of 9 to 10 kilometers of depth in the crust. So one thing, just to recap, one thing that is very important, clearly, is the lithology in controlling the type of the style of the formation you have and the type of fault zone structure you will have. The other important, very important point is structural maturity. And with structural maturity, we mainly mean the amount of shear deformation which is accommodated by your fault zone. So this is a general cartoon which I found it very nice from Perrin et al. 2016, which shows a single fault zone with a principal fault surface, and around here with these symbols here is represented the fault damage zone around the principal fault surface and the fault core. So for a single fault, you can consider in this case a strike slip fault. We will have that the fault have a let's say a long-term propagation direction which is to the right. So you will have that moving from left to the right, the fault is accommodating less displacement, so it's less mature. And you can see that the structure of the fault is clearly changing, I mean, with the change of structural maturity. So from where toward the tip of the fault, the fault is less mature, you have a much larger damage zone, which is called a tip damage zone. Instead, this is becoming more narrow toward the more mature segment. And the other important point is that the fault core material will change. So with more structural maturity, with more shear strain accommodation, you will have more shear strain deformation, more cataclasis, more interaction, for example, with fluid, and generally you will have more localization of the formation. So in general, the rule of thumb, let's say, is just faults that are more mature, so with larger displacement, are exactly more mature and are generally more localized and mechanically tend to be weaker. This kind of concept can be seen for a single fault which propagates in time, but can be also extended to a more general case of a fault system. So normally, this is case, for example, of again of strike slip faults. We will have a single fault propagating, but then at the regional scale, we can have a fault system which is propagating. And then when two fault segments interact, there will be more complexity arising. In particular here, what people do is like that, as we saw before, along a single fault segment, you will have a fault zone structure which is changing depending on the structural maturity. So toward the tip of the fault zone, which is propagating, you will have a less mature fault zone and a damage zone, for example, that here is called tip damage zone. Here you will have a more mature fault zone structure with a more localized deformation, what is called a wall damage zone. And here, where you have instead two interactive fault segments, you will have what is called the interacting damage zone. So normally, when you have two fault segments interacting, you will have an increase, for example, of your fault zone thickness because you will have two fault damage zones interacting and overlapping each other. And so you can see this concept here in 3D. The same concept here exactly shown for, here was shown for a map view for a strike slip fault. It can be shown here for an extensional fault system growing through time. So we will have different fault segments that progressively grow, accommodate displacement. So you will have a more mature fault system developing. At the end, you will have a single fault surface that is connecting all the fault segments with a single fault core also developing. You can see the same concept here for extensional fault zone by again seen in a map view. So you have two different faults with their damage zone, which is here shown in blue, which are progressively growing and extending laterally. And at some point, you will have these two tip damage zone that will overlap, and you will create what is called the interacting damage zone. And at some point, this overstep region, this overlapping region with these two originally isolated faults will be bridged by new fault segments, and you will have a single fault segment forming. So this generates more structural complexity and clearly an evolution of your fault zone structure in time. So clearly the amount of complexity of your fault zone structure depends on structural maturity and the kind of time steps you are in the process of growth of your fault zone, of your fault system. Another important, I think, fundamental factor, which is controlling for sure the fault zone structure and, for example, its thickness, is structural inheritance. And for structural inheritance, we mean in general how coexisting anisotropies or heterogeneities in the crust are influencing the nucleation of a new nucleation and propagation, so the nucleation and growth of new fault zones. This is another nice emblematic example, if you want, from the Central Apennine of Italy. Is again the same fault I was showing you at the beginning, so the Monte Marine fault. This is a seismogenic fault, extensional one. So you will have here the footwall block, and here the hanging wall block, which is represented by quaternary deposits. And is a fault that ruptured last time in 1703 in a very destructive earthquake. What you can see here in the footwall of the fault, all these whitish bands here, is exactly really the basically marking is a proxy of the thickness of your fault zone. So where you see these badlands areas, which are developing at the expense of highly fractured carbonates, is basically marking the border of your fault zone. So you can see that your fault system is in fact represented by two main fault segments, which are left steps. This segment here and this other segment here. And they are overstepping in a region. So you can see already what we were seeing before, that moving from this segment here toward this area of interaction of the two fault segments, your fault zone is increasing in thickness because you have two fault segments interacting, two damage zones that are adding one each other if you want. Then if you move in this area again, you have a very huge increase of thickness, at least apparent thickness of your fault zone. So up here, you are almost 1 kilometer away from the principal fault surface. So it means that you are moving here from almost 50 meters of fault zone up to 1 kilometer here. And if you go to have a look and to do some geological mapping here, in fact, in this area, what happens is that they are outcropping in the footwall of this extensional fault zone some older thrusts. So in fact, in this case, the setting you are having in your case is a bit more complex than a simple extensional fault zone. But if you make a section from here to here, what you are having, you start in time to have like in your crust an original thrust fault, which was your original heterogeneities in the crust. Then you are starting to have extension in your region, but these normal faults basically nucleates in a place, let's say probably in a ramp or in the ramp of this thrust fault zone. And so it interacts with it. And what we are seeing here in this very extensive fault zone here is basically this situation here. So we are basically looking at an extensional fault zone and fault damage zone developed in the hanging wall of a thrust, of a stack of thrust, and in the footwall of your extensional fault zone. So you have an apparent thickness which is very big. And this is a situation we can see very often in the Central Apennines of Italy, that when you have problems of structural inheritance, especially when you have pre-existing thrust, we have a huge increase in the thickness, for example, of your fault zone or your fault damage zone. Another case here, much deeper, or another fault we studied in case here is we are in northern Chile, Atacama Desert. Here we have a faulting which is much deeper compared to below. We are before the fault was exhumed from 2 kilometers depth. Here the faulting was happening between 5 and 7 kilometers depth. We are in granitoids. And the faulting was happening also at much higher temperature between 250 and 300 degrees C. Again, we have a completely different fault zone. We have a different kinematics because we have a strike slip fault. But again, we have a strong influence of inherited anisotropies. In this case, what we can see here marked in this green area represent the fault core of our fault zone, which is green because it's impregnated by chlorite and epidote, which has green minerals. And this one, these dotted white lines represent the magmatic foliation of your plutons, or the plutons form representing your ostrogs. And what you see exactly is that the strike of the fault really is exactly the same of the magmatic foliation. And if you look then at the regional scale of this fault system, which is almost 40 kilometers long, you have two big plutons where the fault system developed, and you can see basically that the sinus strike of this fault moving from south to north is controlled by probably the nucleation of different fault segments along the magmatic foliation with two different plutons, and then bridging and a connection, a linkage between these two parallel segments, parallel to the magmatic foliation segment, which happens with the progressive increase of shear deformation. So this kind of control of structural inheritance on the, let's say, architecture of your fault zones can happen everywhere, from deep in the crust more to the surface. And in fact, then I cannot show you because of time constraints, but there are many recent papers showing this kind of interesting controls of structural inheritance, for example, related to the African rifts. In this case, you have heterogeneities in the older crystalline basement, which are controlling the geometry and the architecture of the current active rifts. The same is seen also in seismic reflection studies studying the rift in the North Sea. Again, you can see that the normal faults that are cutting the carbonates, I mean, in the North Sea, in fact, are controlled by the geometry of much deeper structures that are down in the metamorphic basement. So this is another important point to keep in mind. So this was just a bit of a way, a bit maybe also not well-organized way to show you how different factors, how many factors are really controlling the structure of your fault zone. It mainly is the depth of faulting, the lithology, the maturity of your fault system, and so also the level of segmentation or interaction of different fault segments, and the other, you were saying exactly structural inheritance. So then people tried to put things together, luckily, I mean, and to put together different measurements of fault zone units and come out with, for different faults, with different displacements, so different structural maturity, and they come out with this kind of scalar relationship. Again, you can see this is a paper of Torab et al., which puts together data for fault core. So these are data for fault core thickness against fault displacement for different host rock lithology. So in red, open symbols, you have porous rocks, so sandstone mainly. So we are talking about very shallow faults, fault zones, so less than 1 kilometer depth. The faulting was there. Then you have in blue carbonates, and then you have in black crystalline rocks, so basically granitoids, let's say, or metamorphic rocks. You can see there is a lot of scattering, and this is due to the fact that there are data coming from faults with different kinematics, for example, and also is due to clearly problems, also methodological problems, because people here just measure fault cores, but sometimes there are different, let's say, definition of fault core thickness. I mean, the fault core is measured in different ways. So another source of this scattering can be this. So basically, you can see that there is a power law at the end of the story, relationship between fault core thickness and displacement. And what we can say is basically that the case of non-porous rocks, so carbonate rocks and crystalline rocks, is similar. So they are a bit similar scaling. So for 1 kilometer displacement fault, you have a few meters thick fault core, let's say, in general, on average, let's say, by general talking. Instead, if you go to porous rocks, the thickness are bigger. What is a bit more studied compared to the fault core scaling laws is the damage zone scaling laws. So what people do in different fault zones is like measuring the thickness of fault damage zones. And they normally do it with different techniques, for example, by doing scan lights, by counting, moving away from the fault core, the numbers of fractures you can find For example, in this case, they just count the number of macro scale fractures, and they come out moving from the fault core away. They come out with this kind of power law decay. At some point, arrives to the what is called the background damage level, which is the background damage level of host rock. When you found, let's say, this limit, you can, let's say, establish the thickness of your damage zone. In this case, is 30 to 70 meters, more or less, for this author. Other people do it using not macroscale fractures, but they did it by using microscale fractures or even seal fractures, for example, fluid inclusion of trails. This is a case study. These are case studies from faults in the Atacama Desert in granitoids again. And again, you can come out with this kind of decays, moving from the fault core toward the host rock. And at some point, you are able to establish the thickness of your damage zone. By putting together these for many faults, again, people were able to come out with this kind of scaling laws for fault damage zones, which in general is much more common data compared to fault core, let's say. Again, you have this kind of power law relations. This is for mainly fault zone in crystalline rocks. This one puts together data from different lithologies, so crystalline rocks, also silicoclastics, and carbonates fault zones. And the interesting thing is that you have this kind of linear relationship in a power law, linear relationship. A log-log is a linear relationship between fault displacement and damage zone width, up to generally a few hundreds of meters of displacement, up to 1 kilometer, and then you have a kind of saturation. So this means that at this point, when the fault reaches a certain level of maturity, let's say, what suggests you, I think, this kind of plot is that the deformation tends to be more localized inside the fault core, so you have a much more localized fault core, and you start to passively, let's say, to passively keep your fault damage zone, let's say, inside of your fault zone, and not keeping increasing it. And it is in fact the case of many big faults that, in fact, when you have like faults that have typically tens of kilometers up to 100 kilometers of displacement, the damage zones in terms of thickness are not so different to faults which have, for example, a few kilometers of displacement. And so this is an important thing to keep in mind if you want to have just some ideas of how you can build a damage zone of thickness of small versus small displacement versus large displacement fault. So then there is clearly another important factor which we didn't talk about, which is tectonic setting, which is clearly important because as we saw at the beginning, in different tectonic settings, we have different mean stress values. So the path to faulting is completely different in a compression regime compared to a normal fault regime. Particularly in a thrust regime, you will arrive to faulting. If you think, for example, in your Morse Coulomb space, you are going to create a new fault by increasing sigma 1 typically. Instead, what is happening in a normal fault regime is that the sigma 1 is fixed because it's your overburden, basically. And you are going to fault to in an extensional regime by reducing sigma 3. So these kind of things are clearly, they will somehow influence the level of stress, your fault zone architecture. And then what is very important is also the orientation, clearly, of the principal stress axis, which is completely different in a 3 different regime. So what you will come out, like in a compression regime, you will have this kind of a fault zone system. So this is a case of fault and thrust mountain belts, if you want, in particular the frontal part of a mountain chain. you will have like a classic system of a fault truss system with active decollement at the base, with a very low angle, and then several ramps branching from it. Typically, I mean, moving, I mean, in time, the different ramps start to be active from here, and then the active ramp, the active front of the truss system will be toward the foreland. In some cases, you can have even what is called out of sequence events. So you can have during time some faulting event happening here when still active deformation is happening here. But clearly, this is the way of fault geometries and fault you will expect in a compressional fault system. This is the type of fault geometries you are expecting in extensional fault system. So a segmented several segments of extensional faults that propagate laterally through time, interact each other. And this is a kind, instead of geometries, you are expecting a structurally fault system with typically these kind of structures, which in a contractional regime are called, for example, duplex structure. Again, they can be found also in a strike slip regime. They will be just vertical. They can be called flower structure or duplex structures. And you will have related to different, again, the interaction of different segments of strike slip faults. You can have different local tectonic settings like local transtension, local transpression, and so on. Inside the fault zone, at the end, especially inside the fault core, so where most of the formation is accommodated, you are anyway finding in all these kind of tectonic setting the same kind of geometric array of secondary synkinematic fractures, which are the so-called Riedel shears. So if this is your main fault, typically you are going to produce this kind of array of secondary synkinematic fractures, which are the most common are normally R shears, which are at low angle compared to the main fault plane and synthetic with it, and R1, which are, for example, antithetic. This is the case, for example, in mesoscale fault, when you can see dextral strike slip fault, and you can see this kind of Riedel type are secondary faults that develops inside the fault core. And this kind of scheme you can apply to every tectonic setting. You just need to rotate clearly the system depending on what is the orientation of your fault. Other kind of fabrics that are very common inside fault cores are this kind of fabrics, which are SC fabrics or RCC prime. Normally, I mean, you move from SC to SCC prime with the increase of accommodated shear deformation. Typically, these type of fabric are typically developing inside weak fault cores, so fault cores that are made by phyllosilicate minerals. So you will have the formation of this C-plane, which are parallel to the main fault surfaces, and the S1 with a kind of asymmetry that gives you the sense of slip of the fault. In fact, you can produce the same things if it's in an extensional system. This is less penetrative, the fabric here. This is a fault core of extensional faults in the Apennines, but in this case, inside carbonates and not in clays. So you will have the same kind of fabric, much less penetrative, because it's much more difficult to produce this fabric in carbonates. Why? Because these fabrics are mainly related to slip along phyllosilicate mineral let's say from the planes of silicate minerals and are also related to pressure solution deformation processes in general. So exactly that. Then what I'm going to show you now briefly is like what kind of deformation processes are you expecting inside fault zones, and particularly fault cores, different depths inside the crust, and how different deformation processes are mainly related to different than structural architectural fault zones. So we saw before, this is the classic view of a fault zone conceptual model at the crustal scale, in a brittle ductile regime, and then down here where the viscous root of your fault, where you have crystal plastic deformation. But we are just concentrating here on this part where our deformation is brittle or brittle ductile. So we will have the first, let's say, basically the deformation, the shear strain deformation inside your fault core will be accommodated by fracturing, rock comminution, and cataclasm, we say. So in the upper part, where we don't have cementation, we will have unconsolidated material, so fault gouges, which accommodate this deformation. If you go a bit down, when we have fluids and that cements our rock, we will have comminution and cataclasics. So the main processes that are controlling shear strain accommodation in fault cores in this part of the crust are rock fracturing, comminution, aided by pressure solution. Pressure solution, why? Because inside faults and fractures in the crust, you always have fluids, and these fluids under stress will favor the dissolution of progressive dissolution of mineral, reprecipitating under stress. Particular pressure solution is a deformation mechanism in which a mineral phase, or let's say, will be dissolved under stress in the presence of fluids, and thanks to mass transfer processes, which can happen at local or more large scale, this material that is dissolved will be then precipitated in let's say, dilatant volume or areas which are at low stress. So this is a classic diagram from Renard et al. 2000 that shows you for a quartz, which can be representative of a silicatic crust, or carbonates, which can be representative for a carbonate crust, how two important deformation processes occur. And these processes are gauge compaction and sealing of cracks, basically. And what you can see is that they are mainly controlled by the solubility of the two minerals at a different PT condition in the crust. So you can see that in the upper part of the crust, where the solubility of calcite is higher, you will have that the gauge compaction and the same for crack sealing will be more effective, and their effectiveness will be less going deeper. Instead, the contrary we have in the case of quartz. In fact, quartz start to be soluble in a relevant way over 200 degrees C, let's say. And so you will see that gauge compaction in quartz or in silicatic rocks, we start to be much more important over 200 degrees C, so below 6 to 7 kilometers of depth. And then the silica you will have in solution will be then go to seal the cracks you have open. So just to see that these processes in fact are happening, are occurring in natural fault zones. We have here a view of a fault, or a Venere fault, so it's an active extensional fault in Apennines. Again, you can see a very sharp fault surfaces. And here in the back, you have fault core material. So you have an outer fault core, which is cataclasites, not very well cemented. Instead, normally when you move toward the principal fault surface, where most of the deformation, shear deformation is accommodated, you have a very well cemented layer of fault rocks. And you have typically a cementation front and rocks that are very less and generally less eroded. Also, you can see very nicely in panorama. And this is another example. Is this one again of the Monte Marine fault? You can see a very nice fault surface here. Here below the fault surface, you have the fault core. You can see an outer fault core which is much more eroded here, and this part here which is less, let's say, erodible, which is in relief, which is in fact is strongly influenced by these compaction processes we were talking about here before, no, in this diagram of Renard et al. So you can see that you have all these surfaces which are really pressure solution surfaces forming parallel to the principal fault. So these are the main deformation processes occurring. They are comminution cataclasis, and then pressure solution determining compaction, and sealing of fractures, of open fractures. And again, a type of fault rocks you can have are these very cohesive ultra cataclasites. So this looks like almost an intact rock, but then if you take a hand sample of it and you make a thin section, you will see that these rocks is in fact a very, very strongly comminuted and crushed host rock with big fragments of host rock and all this small white material, which is called matrix, which is made of a small fragment of micrometer scale. And then the porosity is often sealed by cements, by calcite cements. And again, we are going back to these processes of before, so gouge and cataclasites compaction and sealing of porosity, sealing of microfractures. This can happen like this in low porosity rocks, like in carbonates, and the same way it can happen in silicate rocks, but as we saw, at deeper level, depending on the solubility of quartz. Again, instead, if we look at the porous rocks, so if we go at much shallow levels, less than 1 kilometer depth, the formation processes are completely different. We don't have single fractures, discrete fractures that are accommodating easily a lot of displacement. We have deformation and shear deformation, which is accommodated. It's at the beginning along these kind of features, which are generally called deformation bands, which are associated to a porosity collapse, and then different type of deformation, which can become more compactive one, like shear deformation or dilatant, depending on the kinematic of your fault. But in general, you can have these different type of deformation processes. So typically, disaggregation of your rock, so the collapse of porosity. Then you can have, if you have phyllosilicate around, you can have smearing of phyllosilicate inside your deformation band. You can have a start of cataclasis, and then you can have some fluids cementing these deformation bands. But again, these deformation bands are generally very widely distributed inside your fault zone, just because you need much more deformation bands to accommodate the same displacement you can accommodate along discrete brittle fractures. discrete brittle fractures. These are the things that you will find in the field. So this is a kind of system of deformation bands in Iceland, for example, produced just probably tens of meters under the surface in yellow tuffs and yellow clastate, which are rocks which have porosity up to 50%, so very, very porous. If we look inside non-porous rocks, again, we are looking at carbonate rocks, moving away from the principal fault surface. This is the case again on extensional fault. We're moving in the footwall of your normal fault and moving away from your principal fault surface. You will see different units. So in yellow and orange here, we map tens of meters thick fault core units made of cataclasites and ultracataclasites. And then here in this light brown, we have breccia units. So moving away from the principal fault zone, typically, so moving from here to here, let's say, you have a decreasing gradient of strain rate. So you move from ultracataclasites, which are very, very well comminuted rocks where fragments, clasts are suspended inside fine-grained material, to cataclasites, where the clasts are touching each other, and you can have some evidence again of compaction and pressure solution. And then moving more away, you are moving to a breccia unit, when you have basically shattered rocks, which is fragmented, affected by network extensional fracture, but not accommodating a lot of shear deformation. And then moving more outside, you're moving inside what is called a damage zone. So this kind of rocks that I'm showing you now, not porous rocks like carbonates, but the same can be for silicatic rocks like granitoids and so on, are, let's say, strong rocks. So the rocks that, according to the Byerly studies, have the Byerly friction, static friction of 0.6, 0.7. Then, so inside of these fault rocks, typically, you produce this kind of fault structure, which is the fault structure of a strong fault zone, what is called a strong fault zone. Many other faults instead are characterized by fault cores. I mean, depends. I mean, there are fault zones that are developing inside of very weak rocks, host rocks, like the Carboneras fault I was showing you at the beginning, the paper of Faulkner. This fault zone is developed inside very weak rocks, which are mica schists. So you will see, you will produce a fault zone inside this kind of rock, which is very large, with a very distributed deformation, and which will be very weak because the material in which it develops are weak. And for weak, I mean rocks or formed by minerals that have static friction, which is much less than Byerly. So friction that goes from 0.1 up to 0.3. And this kind of minerals or minerals forming fault rocks can be, for example, clays, can be phyllosilicate in general, for example, serpentine, and so on. So you have this kind of other category of fault zones, which are weak fault zones, which can be weak just because they develop from weak protolite, or can be weak just because during strain localization or fault maturity increase, we have, for example, starting from a siliclastic, strong rock, we have a progressive comminution. Moving toward the principal fault surface, we have the formation of ultracataclasites. If in this fault, as normally it is in the crust, reactive fluids are percolating, this fine-grained material can interact with the reactive fluids, mineral transformation can happen, and typically alteration products from silicoclastic silicatic minerals are clays, are chlorite, are serpentine, for example, from metamorphic rocks, which are these phyllosilicate minerals, which are platy minerals, which are intrinsically weak. So basically, you can have weak fault zones develop strong protoliths. That's because they are very mature fault zones where there have been fluid rock interaction, mass transfer, and progressive fault zone weakening. Again, in this kind of fault zones, the formation mechanism, differently from the strong fault we saw before, is not much brittle comminution, formation of cataclasites with fragmented rocks, matrix, and cement, but is more pressure solution. And pressure solution accommodated really by slip along this progressive slip along these phyllosilicate mineral plating minerals. And these, for the seminal papers of Gratier, are two types of pressure solution mechanisms that are thought to be able to accommodate shear strata formation in large, weak faults that can be also lithospheric ones. And this can be this kind of mechanism in which there is slip along the phyllosilicate mineral plates, and then the material that is dissolved along these planes by pressure solution is then precipitating inside cracks kinematically formed. Or then you can have also mass transfer due always mass transfers done, I mean, and by a fluid that occurs not in fractures, in kinematic fractures, but along grain boundaries, for example. And is another case of, for example, fault zone developed in serpentinites, or, for example, here, thrust fault zone, very weak thrust fault zones developed in marly carbonates in the Central Apennines, where you have basically a fault zone which has a very little damage zone around, and all the fault zone is made of 10 to 20 meters thick, very deformed fault core with this kind of very penetrative SC fabric. So all the shear strain deformation along in this fault and the displacement that can be also the order of tens of kilometers are accommodated inside of these packs of a few meters, up to tens of meters of phyllosilicates material. And these are weak faults, which has this kind of peculiar and typical fault zone internal structures. Again, going back to the beginning, people model in the lab, measure in the lab, for example, what is the frictional behavior and the strength of what can be a weak material, in particularly the realistic weak fault zone material, which can be a combination of a strong phase, for example, quartz, and a weak phase, for example, clays. And what you will end up after the experimental data, after some modeling, is this kind of thick line which models represent the strength profiles you have along a weak fault with a fault core made of this material, which in the upper part, which will be controlled basically by the frictional behavior of a strong phase, which can be, for example, quartz. And if you go deeper, then instead the strength of your fault will be instead much more controlled by the behavior and the frictional behavior of your weak phase. And in this case, the deformation mechanism is considered to accommodate deformation in this kind of mixed full rock material is again pressure solution, creep, pressure solution, creep, so deformation by pressure solution. This author model their experimental data for different kinematic setting, strike slip fault, normal fault, thrust fault. You can see that things change a bit, no? But the message is the same at the end. Then just very briefly, this is a bit of another world of faults, let's say. It's typical setting where you have high fluid flux, so high fluid pressure. And in this kind of situation, you can have that faulting is mainly controlled by, in fact, the level of pore fluid. And so the faulting is mainly controlled by if you think of a Morse circle, by the moving of your Morse circle toward a faulting criterion by increase of fluid pressure. And this increase of fluid pressure can be cyclic. I mean, so you can have faulting, fluid driven and associated to pore fluid pressure oscillation. This is a classic case, for example, of for example, I don't know, in the thermal fields where you have swarm activities, stuff like that. And in terms of fault rock record, things that can remind this kind of behavior where you have this kind of fault core material. So again, you have cataclasites, ultra cataclasites, but in this case, the clasts that derives from the comminution of the host rock are not let's say, suspended in a fine-grained matrix, so material that was finely grinded and crushed by the fault movement, but is suspended inside of cement. So this white material here, in this case is quartz, in this case is dolomites, is just precipitated from a fluid phase. So this typical fault rocks tells you that you have a kind of tectonic setting in which faulting was associated to high fluid flux. You have the latent structure, and you have the ingression of cataclasics and the ingression of fluids, and the typical formation of these fault rocks with, for example, suspended clasts in cement and so on. And the mechanics of this kind of rocks is a bit different. The structure and the architecture of these faults also is a bit different. For example, many fault zones associated to ore deposits in geothermal, like epithermal or mesothermal ore deposits, are associated with this kind of fault zones. So if you want to know a bit more of this kind of peculiar fault zones and fault zone rocks, I suggest you to read these papers of these big professors like Steve Cox or Rick Simpson. I mean, they're now retired, but they did very, very fundamental work on this kind of peculiar structures. Then just to end all of this, since you are going to study fault zones and fault zone structure in relation to seismic cycle, let's say something about, let's say, how you can probably, from the rock record, let's say, where you can see in your fault zone components, in your fault zone units, where you can see the different phases of your seismic cycle recorded. So this is a classic general view, I mean, a seismic cycle for a fault or a fault zone, in which you have, for example, this is in red is the variation in time of fault strength in a fault zone, and this is the shear stress inside of your fault zone all along your fault plane. So you will have, for example, in a seismogenic fault that due to the, let's say, to the progressive increase and storage of elastic strain energy, you will have an increase of shear stress along your fault at some point where your shear stress reaches the strength of your fault, you will have, for example, an earthquake, a sudden faulting event. And if you look at the slip on a fault, you will have a sudden event of seismic slip. And this slip happens in a few seconds, like it's something very fast. Then after your fault ruptured and slipped co-seismically, you will have what is an interseismic period. It can be very long, it can be tens, hundreds of thousands of years, depending on your tectonic context or your faults. And inside of this period, you have other kind of processes which are healing processes, so processes that are able, are able to make the strength to recover, to have a strength recovery of your fault zone material. Then you can have a lot of different behavior. In fact, in your fault can be kind of locked, like in this case, during the interseismic. During interseismic can creep a bit or so on, but it's a different story. So let's see what happened, for example, during co-seismic slip, so during an earthquake faulting event. What is expecting normally like you are rupturing pre-existing faults, no? Most of the cases, so you have a fault which is loaded under certain stress field, then you have an earthquake. During an earthquake, what you will have, like your faults rupture. So let's say that your rupture propagates from left to right with these kinematics, and you will have a rupture front which propagates very fast at a velocity of the order of 2-3 kilometers per second. And we are talking about a few millimeters to centimeters. So the fault of the rupture tip, you will reach stresses of gigapascal. You will have high strain rate loading and of the rock, which are able to dynamically fracture and even pulverize your rock. But in fact, what we know is like that this kind of dynamic loading you can have around the propagated rupture tip in your dynamic loading of your wall rock. Let's say the extent and the magnitude of this dynamic loading depends, generally depends on many factors, but is mostly related to the velocity of the propagation of your seismic rupture. So if you get the, let's say, the extreme case of a super shear rupture, these are like a snapshot of a rupture simulation, dynamic rupture simulation of a super shear rupture in different moments of its propagation. These things represent the dynamic damage is produced in the wall rock. And you can see that in a case of a very fast rupture, like a super shear one, you can dynamically load your rock at very high strain rate, even at tens to hundreds of meters of distance from your principal fault zone. And in fact, that's what happens, let's say, when you have rupture propagation. Then what happens when along your fault that now is free to move as a rupture, is like co-seismic slip will happen. So the two blocks of the fault we will move one with each other, normally at an average velocity of 1 meter per second. And on this fault plane, you will have a lot of in fact, most of the elastic strain energy that is released during an earthquake will be dissipated here along this frictional interface by frictional heating due by friction. And this frictional heating, let's say, wave, it's a transient one, is responsible of producing many dynamic weakening mechanisms are controlling basically the dynamic of your rupture propagation. These things, like this co-seismic slip, happens typically thought to happens really on very, very localized slipping zone, which can be of millimeters of micrometer in thickness. And so if you then look at your fault rock record, so at your fault zone exhumed now in the surface, what you will find, for example, if you are looking for rocks in granitoids, you can have the formation of these black, tiny, thin layers, which are layers of frictional melts, which are typical fault rocks called pseudotachylite, that are the only now clear geologic evidence of past coseismic slip on a fault, let's say. So you will see that you have your mostly intact rock around, and here the evidence of for sure ruptures that have been propagated along this fault, but then what you have is evidence of frictional eating, so coseismic slip. In the case of other rocks, for example, we are talking about carbonates. Again, we are expecting the same. So what we're expecting during coseismic slip, we are expecting extreme shear strain localization. So if we are going to look for the scars of these, let's say, processes in the rock record, we will trying to look just at the few centimeter to millimeter below the principal fault plane of a carbonate fault like this, for example. But till now, let's say, in natural faults in carbonate, there is not, we didn't found a smoking gun of this frictional eating associated to coseismic slip. This is, for example, what is produced in experiment, in rotary shear experiments, in calcite rocks. So you produce this thin micrometer thick layer of plastic, crystal plastic deformed calcite, which is almost a myelonite, so a viscously deformed layer. But till now, I mean, in the nets of these kind of things, we never found them. Also because then, especially carbonates, fault rocks are strongly obliterated by other processes like pressure solution. We are acting, for example, during the interseismic period. Then another things instead that we are seeing that can, let's say, leave some scars, some evidence in the fault zone record in exhumed faults is the dynamic rupture propagation. In the sense that we said that when we have a rupture propagating along a fault, in this case is a more common sub-Rayleigh rupture. We have a rupture propagating. Around the rupture tip, you will have a dynamic loading of your host rock. And so what you can easily calculate, for example, is at what distance, what kind of dynamic strain rates you are achieving at which distance from your principal fault. So if you think your master fault plane is here, and this is the increasing distance away from your fault that is rupturing, this is the decaying of dynamic strain rate that you are achieving in your host rock. And from rock deformation experiments, we know that in the lab, we are able to dynamically fragment and fracture rock, especially like non-porous rock, at strain rate of the order of hundreds to the second -1. So this means that for a general sub-Rayleigh rupture speed, we can, let's say, dynamically pulverize and fragment our rocks at distance, let's say, of few centimeters from the main fault plane. But then if you go along big lithospheric, in case plate boundary faults like the San Andreas, they have been historically described fault zone material like these, which are exhumed from very shallow depths, less than 1 kilometer in general, which are the so-called pulverized rocks. So around the San Andreas fault, you can find an exhumed shallow structure of the San Andreas fault, which is made of hundreds of meters of thickness of a granite looking like that. that if you look at it like that, it seems an intact granite. But if you go with your finger in this granite, we can dig it out like a sand. Basically, it's a granite. It is exploded. It's like extensively fragmented down to the crystal size scale. And this happens up to hundreds of meters away from the masterful plane, and is thought to happen during multiple rupture propagation along these plate boundary faults. In the case of the San Andreas, let's say, probably people say during super shear rupture that can really dynamically load rocks at high strain rates at these large distances. But in fact, if you go in the Apennines, even in Dolomitic fault zones like these, again, is the Monte Marina that I show you many times during this presentation, you can find outcrop depth with hundreds of meters of thickness, again, of dolomite, which is completely shattered. It's not pulverized like to the powder level, but is fragmented in fragment from centimeter to the micrometer scale without any shear deformation. So it's not a cataglasite, it's not a gauge, but it's a rock which is shattered, is exploded. You can see it here in a kind of detail. This is what we call geologists the third nodule, which has this kind of elliptical shape needs originally, and the rock is just shattered. This body maintains this shape. It's just opened by many fractures sometimes and are sealed by cement. So how can we deal with this kind of, how can we try to explain this kind of things? We don't know. But this kind of damage zone can form during long-term stable propagation and growth of fault zone, but can also probably also, let's say, record some processes happening during rupture propagation. In this case, it's difficult to explain them probably due to statistically super shear rupture propagating along these faults, because the faults we are talking about in the Apennines are much smaller than the San Andreas, are 15, 20 kilometers long. The displacement, total displacement is 1 kilometer, something like that. So it's difficult to think about this kind of models. But for example, we can think about other more complicated models like that are being suggested by recent rupture dynamic simulation. So for example, if you just make a rupture dynamic simulation, and a group of Ampuero, Wang, these people did some work on this, not on a homogeneous, starting from an homogeneous elastic medium, but starting from a fault zone that already has its own heterogeneity. So for example, as is embedded by an original damage zone, which can be modeled as a low velocity zone with degraded elastic moduli. They could see that just by propagating more, let's say, classic subrailic ruptures along these faults, the ruptures start to have, let's say, weird feedbacks. So due to the presence of these low velocity damage zone, pre-existing ones, and depending on how sharp are the boundaries and how big is the size of this damage zone, the rupture can increase its velocity. You can have multiple rupture pulses originating from a single one. You can have transient passes to subrailic to super shear rupture speed. And so maybe you can think to having statistically this kind of scenarios happening on your small but structurally complex fault to also produce some this kind of damage, partly dynamical. Another thing is aftershocks. Aftershock sequences, in the sense that maybe we can see even in our fault damage zone, especially in the very thick ones, that, for example, some of the one we have, we recognize in the Apennines, we can even see probably something that happens during the aftershock sequences. This, for example, is the L'Aquila fault system that erupted in 2009, just imaged by all the aftershock happening after the main shock. You can see a very complex fault geometry that is activated by aftershocks. for example, at this depth, you can see many fault segments that are just spaced apart several hundreds of meters that can easily be, like, for example, a principal fault and then some secondary faults inside of a damage zone, for example. Or again, we can see this again is something that happens in a L'Aquila sequence that is rupturing an extensional fault system in an extensional way, like this. We are clearly seeing like the illumination of this low angle structure that very likely are all the inherited thrust fault zones that have been activated by aftershocks in extensional way. So if you think again at our model before the Monte Marine fault zone, which is exhumed from 2 kilometers depth, we are almost looking at the situation here where we have a very thick damage zone. We have looking in the footwall of the extensional fault zone, in the hanging wall of the thrust zone, and you have a very, very thick fault zone. And the case, like very conceptually, can be that you have like a main shock happening here and then several aftershock happening in your secondary faults, which can be also inside, we can occur inside of very thick damage zones sometimes. So maybe aftershock can leave also a record or the activity in fault zones. Then there is all the part of post-seismic healing, how you recover the mechanical properties of your fault zone during the seismic period. And again, we can get information from lab. So people typically in the lab, I am not going in detail about these things because I think there will be lectures about these rock mechanics aspects done by much more expert people than me in the future. So one thing that can happen, and I can explain the regain of frictional strength of along a frictional interface is what is called frictional healing, and what is studying a friction experiment in the lab. So basically you can have, after you stop the sliding after an earthquake, and your interface or frictional interface is like statically in contact, you have an increase of the friction in time, and typically this increase goes with the logarithmic of time, or the hold time is called. And different fault rock materials, different materials have different behavior. So you typically have a strong cataclastic material like carbonates that have a very high frictional healing. Instead, you have a more, let's say, weak rocks, as we were saying before, all these fault cores made of clays or serpentinite and so on, that have very little or basically null frictional healing. And when we are talking about, in this case, frictional healing, these are just tribochemical processes probably happening really at the interface, at the atomic scale. And they are probably, I mean, they are responsible of an increase in strength of your fault that goes with the logarithmic of time, logarithm of time. Then there are other processes that can happen inside of your fault core, not only along individual fault interface, but even volumetrically inside your fault volume, which has been fractured and microfractured during an earthquake rupture. And these processes are instead, again, gauge compaction due to by pressure solution and mass transfer, and especially sealing of fractures or microcracks by mineral precipitation. And these is, for example, so you have like a shattered brates and dolomite with fractures sealed by calcite. And this kind of processes normally related to gaining cohesion of your material, strengthening your material, are much more effective in strengthening your fault, because in fact, in general, the regain of strength is more linear compared to before. So these are kind of processes that can be recorded in fault zones, inside the fault core materials, but also probably inside of the damage zones. And again, then I'm going to stop, and here again, there will be other people for sure that we can talk about these things better than me. like Giulio, Andrea Niemeyer, and so on, like the supervisor you have. Another important thing to consider, and many of the people doing model will consider this kind of things, mechanical behavior of your fault material, is the frictional stability. So what is the response of your fault material, in this case normally is your fault core materials, to a change in loading rate. And you can have different regimes. So a typical case in which by increasing loading rate, the friction is decreasing, and typically is an unstable regime, is an unstable regime like this, which typically is a case where is a regime where you can nucleate earthquakes, and then is a contrary, the opposite regime in which instead the friction increase when you have increase in loading rate, and you have what is called the frictional strengthening behavior. And typically in this kind of condition, you are not able to nucleate earthquake, and this happens normally down, I mean, in the clearly in the viscous part of your fault zone, and also typically thought to happen also in the very shallow part when you have very weak material, very weak minerals, and fault core materials like phyllosilicates, clays, which have this kind of behavior. So I stop here about this part, and I wanted to talk about this a bit about the extensional setting and the sinusonic fault zones in the Central Apennines, but maybe we can organize something later during the year where before we are going in the field, if you think it can be useful. So thank you, and sorry for the this bit of disorganization, but that was what was it. So if you have some question and some things that were not clear, I mean, maybe I can.
Thanks a lot, Michele. It was really exhaustive and very long.
Sorry. Yeah.
No, don't worry. That's
was a bit in a rush. I put together a lot of material, and then I was a bit lost in.
Okay, I hope we have some questions from the students. Do you have some questions?
Yeah, maybe I have a question.
Yeah.
At a certain point, you mentioned how the maturity of a fault is related to the amount of slip that it can accommodate.
Yeah.
And so I was wondering if there is also a relationship between maturity of a fault and slip rate, not only slip.
That's a good question. I mean, again, difficult to answer. As you saw during the presentation, I was a bit messy because all the things, the factor I show you, in fact, they are interrelated. So there are feedbacks. There is a lithology which is related to the depth of the things and so on. So I would say maturity, in my view, mainly goes with shear strain accommodated, so displacement accommodated. So we'll, from a less mature fault system to a more mature, we will move from a geometrically more complex system to geometrically more simple fault network, let's say. And I would think that if you have like a crustal scale fault, what you should have at some point, you have a linkage with different segment producing a single fault segment connecting each one. And then at some point you will have a single fault core. And this fault core material at the beginning, it will be formed by the, let's say, by your fault rock around, let's say, that is just crushed. But in the long term, you can have like a lot of comminution, a lot of shear strain, so a lot of fine-grained material, which is more reactive, for example, with fluids. And then typically is what happening in terms of full weakening processes in the fluid rock interaction in this kind of fine-grained materials led to mineral transformation. For example, starting from silicatic rocks to produce clays. And clays are weaker, lower friction. So you move from beginning more strong faults where was less mature to a weaker fault when it's more mature. And ideally, if your loading condition, your boundary condition are a bit the same, ideally you should think, for example, that you are progressively increasing the velocity at which your fault is moving. But then the point is that there will be other feedbacks entering, and so it's not generally the case. I mean, because in fact, most of the case, this big mature fault like San Andreas, with this clay mineral fault cores, the carbonaires I was showing you, very thick, are very weak, and many times they are big sections which are creeping, for example, which are move very little. So they accommodate more than the strain rate, I would say. You change the style of faulting. So probably you will move more to in a very mature and weak fault zone. You will tend to have more creeping behavior. Instead, in a more strong section your fault, you will tend to have like let's say a more locked fault, for example, when you can instead for example, increase the stress you accumulate on this segment and then abruptly rupture it in earthquake. And it's what is happening, for example, very naively explained now, but it was happening, for example, in San Andreas. They have a lock section in the south, they have a big creeping section in the Parkfield area. And in fact, this section is full of saponite, is full of clay materials that they found in Safford, in the drilling project they did in these fault zones, really to understand the paradox and how a single fault can fault in different style. Let's say, I mean, can. So I don't know if I don't know. I don't have an answer. Let's say to say really to answer you about the increase of strain rate, which in fact theoretically I mean would make sense, but I think then other mechanisms start to play a role, maybe.
Thank you. It was clear.
Other questions? Okay. No other question. Maybe we are also quite tired, but remember that we will have the record of the presentation, so we can rewatch if necessary. And obviously, I think Michele is available for any question also next days. And maybe, I don't know, Michele, can you share also the presentation, maybe a PDF of your presentation, your slides? Could be useful.
Sure. I will share it. If you think it's useful, maybe I can, at least for the main papers, some are very classic papers. I can share you a folder on Dropbox or wherever we are using.
Okay. I think we will discuss next week in the annual meeting. Maybe I was thinking to create a Zenodo page where we can put together everything and share everything. So, okay, we will have the instruction soon. We decide next week when we see it together. I don't know if you will come next, Michele.
No, I cannot come in Ax, but Giulio, I think, will be there.
Yes.
No, but I will join next lecture for sure. And yeah, thanks to everyone. And sorry for was a bit disorganized, I think, but I hope that.
No, that's okay. I stopped also
yeah.
the.
I can send you the material, and maybe you can.